in 10 seconds. Hello and welcome back to Calculus 2. We are going to talk about 8.6 alternating series whose form will look like this. Can start at 1, at 0, somewhere. And an example of that one would be, let's say, negative 1 to the n divided by n, going from 1 to infinity. So like alternating, hyperbolic, something like, alternating hyperbolic series. Harmonic series. There. So how do we solve these problems? You will peel off an only and look at an first. If the limit of an is 0, as n goes to infinity, and the sequence an is decreasing, you will enter the convergence branch. If those conditions do not hold, you have divergence right away. On the convergence side, further, you will check summation of an. Observe that there is no negative 1 piece there. So just an. That's a different problem than the original problem. And that problem can either converge or diverge. The result would be, if it converges, absolute convergence. And if it diverges, conditional convergence. Here, con. All right, so that is the method of how we solve this. So now, to take a look at my problem, I can rewrite this problem as the summation of negative 1 to the n times 1 over n. So my an is 1 over n. I will check the limit of 1 over n as n goes to infinity, and I will get 0. And I know that 1 over n is decreasing. So I have both conditions check off, which means that I am entering the branch of convergence. Now I check summation of 1 over n, and I know that summation of 1 over n diverges by p series. So the path that I took to solve this problem is I started with an, traveled down the convergence branch because both conditions were good, and then the summation of an diverged to give me conditional convergence solution for the problem. So I hope you can follow the tree that way. So you will only look at an piece, test the two conditions, and then you go down one of the two branches, convergence branch or the divergence branch. If you're divergence, you're done, right? If any of the two conditions fail, you're done immediately. But if they both pass, you have to check the summation of that an, and then that one will either converge or diverge. So if you have a convergence followed by convergence, it's absolute convergence. And if you have this convergence branch followed by the diverging series here, you have conditional convergence. Now, a lot of people, now I have to write the answer here. So answer, remember we write essays in this class. So answer is, since the limit of an is 0 and an is decreasing and summation of an diverges, series negative 1 to the n over n converges conditionally by alternating series test. So you have to write all of those things because they're all part of your theorem. Your problem has to go in a limit to 0. Your sequence has to be decreasing. And then if you get the divergence like we did on the series part, then you have altogether conditional convergence. So we followed the branch one more time this way this time. That was the way we moved through because that's how conditions worked out. Now, the reason why I do this problem first is because we know from before that summation 1 over n diverges by P series or integral test, right? Pick. And we call that harmonic series, right? That's a let me just write it. So harmonic series. Now alternating harmonic series, which is this, converges conditionally. Now a lot of people are like, what is the meaning of converges conditionally? You can technically see that some of the terms there are actually 1 over n, right? So under which condition this converges? Under condition that it's alternating. If this series is not alternating, it diverges. So you will see as you go through the problems in this chapter, in this section, that anytime you have alternating series and you get conditional convergence, as soon as you remove that -1, it diverges. Which makes sense. Which makes a lot of sense, right? Because that's exactly what you computed. You computed the alternating series without alternating part. It diverged. So it's common sense that you're going to call it conditional convergence because it's a convergent branch. And if it doesn't have the convergent piece, it diverges. Therefore, it converges on the condition that the alternating piece is there. And then if you get convergence either way, then it's absolute convergence regardless whether the alternating piece is in or not. You will make much more of sense of this, what I said, once you listen to the stream 15 times in a row if you need to. And it will eventually click. Cheers. Good. Good year. No, I'm serious. Look. Right? Right. Who knows? Thank you. I said thank you. You're welcome. The next piece is I told you already in the previous lecture that when you have cosine n, cosine 5n, cosine of n squared, or anything like that, you can ignore it in a problem because it's always bounded between 1 and -1, and it's going to be very rare for you to actually hit +1, -1 values, or maybe you will never hit depending on how the numbers work. But if you have cosine of n pi, this is exactly the same as writing -1 to the n. What is n pi? So what's cosine of pi? For n equals to 1. What's cosine of pi? -1. And what's when n is 1 on the other side? What's -1 to the 1? -1. For n equals to 2, what's cosine of 2 pi? 1. And what's -1 squared? You see how they are producing the same numbers? So if you want to be fancy, you can write -1 to the n as cosine n pi. And that becomes alternating series. So previous problem that I had, right, was -1 to the n over n. I can write that problem as cosine n pi over n. It's the same problem. It's the same problem because of this. Now you can pull this off as well with sine n pi over 2. It does the same thing, except n pi over 2, it starts at 0. So this is going to be -1 to the n plus or minus 1. So here, whatever. All right, so they're equivalent. They're the same. So this is what we get. Okay. So you can have these to do the same thing for you. So these are the ones that you have to be careful, right? But if you have cosine to the n, you can just ignore it. I mean cosine of n. So watch for them pi's, right? Okay. Let's solve a few examples from the textbook. We have what, another 5 minutes left, and then another 20 after that, and we are done with the section and the chapter. Where was the textbook over here? He's getting it, and if you say the words, you'll just owe more money. So think of it, me saving you money right now. I think I have enough. You have enough money? Okay, it's $10 per mention. Wait, you owe 10 and you owe 10, right, so far? That's 20, yeah. Twice, then $20.
Me?
Yeah.
No, you owe 10 if you still don't like it. That's a joke for
Okay, so let's take a look at let's start with problem 14. 1 plus 1 over k, yep, 2 viewers. Okay, there we go. All right, so this is the first example we're going to take a look at. You have the tree over there on the board. So you're starting with realizing that ak is equal to 1 plus 1 over k to the k. You are going to go down the branch, see what happens when you take the limit and is it decreasing and all that stuff.
I looked up and I saw it. Well, I don't know if it's so bad. Jesus Christ. Yeah, I suppose I could, but how would that help in this situation? Could you root test a sub? Oh no, because you're looking for what happens? No, where in the vicinity? Oh, we're going towards like Harmonic Series. So, wouldn't that just mean that this? Yeah. No, May. Yes, I'll be here still. It's June. May what? May what? May what? Oh, yeah.
Yeah. I know, I was bored.
I'm almost 21 years old. You know, I've only seen references to it. Yeah, it keeps legal. I've only seen references. Yes. She just put a link there and she put.
I also know that we go together.
She's dying.
I also know that, like, I think it was last year that.
All right. What do you have since you are all partying already? Divergence, very good. So it's a very quick problem. It's divergence immediately because the limit of 1 plus 1 over k raised to the k is equal to e. That's not 0. Done. D stands for done, right? No, D stands for divergence. Right. That was problem 14. That was quick. Let's see, next problem. Problem 18, because we can.
A lot of things we can do, but not a lot of them we should.
I see. Yeah. Here's the next problem. It says summation 2 to infinity from of negative 1 to the k, ln k divided by k squared. Is it convergent absolutely, or conditionally, or divergent?
You don't have to do that. It's just slow and fast. That's it.
Done. Exactly. Very good. You use the growth rate of functions. It's slow or fast. It goes to 0. Done. All right. So AK is ln k over k squared, which means that the limit of AK, which is the limit k goes to infinity of ln k over k squared, you can go with the growth rate of functions. So slow divided by fast is going to go to 0 immediately. And is it decreasing? So now, is AK decreasing? So now you have to figure that one out. Now, we know that the denominator grows much faster than the numerator, so of course it's decreasing. But I want to show you a formal proof for this, because these decrease proofs show also in the integral test, and also you have the similar proofs when you show that AK and BK, right? The relationship between them for comparison test, direct comparison. So let's see. I need to show that AK plus 1, which is the next term, is smaller than AK. So I need to show that. That's how you show decreasing, when the next term is smaller. And then the next term is smaller still, and the next term is smaller still, so it goes down, it decreases. So what we are going to do is we are going to create the ak plus 1, which is ln of k plus 1 in parentheses divided by k plus 1 squared, and that needs to be smaller than the original ln k over k squared. So we can, now I'll show you another way. If this one doesn't pan out, we have another way. So cross multiply, you get k squared. ln of k plus 1 should be smaller than k plus 1 squared over, and then ln k, right? So now, if you look at this side is k squared ln of k plus 1. The other side has k squared plus 2k plus 1, and then ln k. I hope that you see that this over here is almost the same as this, but this side has also this left, right, when you distribute. So it's clearly bigger, right, because you still have that extra k there that grows. So this is a proof already, but we can do better using derivatives. Remember how when you have ln k over k squared, if I am able to show that the derivative is negative forever, so I move this into ln x over x squared, and I take the derivative of it. So now I take the derivative of ln x divided by k squared. Now if this thing is always negative, we're good to go. Let's see. So the derivative of this would be, we have k to the 4th in denominator, and then I have k squared over here. Copy the 1 over, oh, sorry, not k, these are x's now. Sorry, x. So this is x to the 4th, and then x squared times 1 over x minus ln x times 2x. What I can do is I can cancel one of the x's here. Maybe I should do that different color. So cancel one of the x's, and you get, to factor the other x, you get 1 minus 2 ln x divided by x to the 4th. So what you get at the end is 1 minus 2 ln x divided by x cubed. So that's the derivative. Now you can see that it's always negative, right? Because we start at ln 2. ln 2 times 2 is bigger than 1. So we have a decreasing. So you can use the derivative as well. And that's it. Wait, ln 2 is not, yeah. What's ln of 2? Yeah, but what? Yeah. So there you go, it's decreasing, right? So now we proved that the limit is equal to 0, and we proved that it's decreasing. So limit ak is equal to 0 plus ak is decreasing. So we are good now for the convergence branch. Now we are going to find the summation of the problem without negative 1 to the n. Now we're dealing with ln k over k squared. Starting from 2 to infinity. So how are we going to do this one now? That's the trick, guys. You see that summation an there in the middle of the tree? Any of the 9 tests that you learned so far can happen there. Yep. And in this case, which method should we use? We can use ratio, we can use comparison, right? So let's try ratio. Might be easier. So AK, so let's try ratio, So AK is equal to ln k over k squared, and BK, or sorry, AK plus 1. I should do this also by comparison test. AK plus 1 is ln k plus 1 over k plus 1 squared. So we have the limit of k goes to infinity of ln of k plus 1 divided by k plus 1 squared times k squared over ln k. All of these functions have the same growth rate. So the limit over here is exactly 1. Test is inconclusive. So we can't use ratio test. Okay, try comparison. Why do I want to try comparison? Because ln k is similar, like writing square root of k, which is actually k to the 1/2 exponent. So if I'm choosing a bk, I will choose bk that it's k 1/2 divided by k squared, which all together is 1 over k to the 3/2, which is summation of bk is still convergent by p series because it's bigger than 1. All I need to show is that bk is bigger than ak. Oh no, just do the limit. What the hell? Limit. So limit, we do the limit comparison. Of k goes to infinity, we have our original problem, which is ln k divided by k squared. All of that divided by 1 over k to the 3/2. So now that limit works out to be what? K goes to infinity. I have k to the 3/2 times the ln of k divided by k squared. So this works out to be the limit k goes to infinity of ln k divided by k to the 1/2. It's slow over fast. Limit is 0. Right? Because ln is slower growing than any exponent, right, on k, which is like a polynomial looking one. So we have equal to 0. I'll put in parentheses growth rate. So we do have that both will do the same since bk larger than ak and summation bk converges and limit equals 0. We have that the summation of ln k over k squared converges by comparison. limit comparison. Need to put the limit comparison. So now that I know that all that converges, I can write the answer for the problem. Since limit ak equals to 0 and ak is decreasing and summation of ak converges, problem, which is negative 1 to the k ln k over k squared, absolutely converges. So absolute convergence by alternating series test. These are awesome, right? Look at that. 15 minutes to do it. I will give you 2 minutes to catch up writing, and then I will go through the entire problem and then release you upon the world. Then I will explain the problem and you will. Yay!
Are you gonna be here tomorrow? Sure. Why wouldn't we be here tomorrow? We still have physics. You want to do it? I'll do it tomorrow. Yeah. Of course.
Do not leave without giving the tests if you want the grade. All right, let's recap this problem and then do the exam stuff and leave. So let me find where this is where it starts. After the class. This is where the problem starts, and we immediately realize it's alternating series because it has alternating term. This alternating term will alternate between positive and negative on each next term. We immediately isolate AK from the problem because we need to test that AK and make sure that as we take the limit going to infinity, the limit is 0 and that it's decreasing. It has to fall both of those conditions. So we saw that just by, right, as Ryan said, we should take a look at growth rate of functions, and we see that we have slow over fast. That's immediately by growth rate of functions, limit is 0 and the first condition has been met. The second one you can either do by using algebra, or you can do by using calculus, taking the first derivative, making sure that the first derivative is always negative. So if you use any of those two methods, you will be able to prove that the sequence an or ak is decreasing. Once those two conditions have been met, you are on a convergence branch, and now because you are on a convergence branch, you need to figure out what's happening with summation of AK. So this is just, you take away the alternating series term, which is negative 1 to the k, and then you test this one. Now, while testing this one, you can have comparison test, root test, ratio test, divergent test, geometric series, integral test, God forbid, right? So you can have any of those tests there. And in this case, we tried ratio. Ratio didn't work out because we got limit equal 1, and that's when the ratio is inconclusive. Sure, abandon that, move to the next one, comparison, and I used the limit comparison test. Now, you know, I said ln k and root k are nearly the same. Root k grows faster, but root k and ln k, when you graph them, they don't look that much off, right? The square root of x looks like this, and the ln x looks like that, so, you know, they pretty much catch up, right? Because this is at 1, and over here at 2, they're already, right, leveling some kind of. But, you know, square root will still grow faster, but they're, you know, there. So now when you try this, right, we know that the BK that you picked is convergent by P series because the exponent is larger than 1. Crank the limit, we get growth rate of functions again, we get 0, and we establish that we have a convergence on that part. So this is the entire problem from previous section 8.5 on comparison done as a part of the alternating series. And now we write the overall answer to the entire problem by simply pulling all we know. We know that we passed the condition on 0 on the limit. We know that we passed condition on decreasing. We also know that the summation of AK, which is what we just did, is convergent. So because all of those things channel this way, right, we have absolute convergence. Because here are the two terms, then you did this, you got that, which leads the branch into absolute convergence. So all of the 10 tests are absolutely convergent. You have in the alternating series, you also have conditional convergence, and then they all divergent, right? So all of them have the choice between convergent and divergent, with that convergence always being absolute convergence. And the alternating series is only one that also, in addition, has conditional convergence possible. So this is chapter 8. Look for the project tonight. 3 problems. You will have to pick. So there will be 2 documents. One document with problems and one. Now, there will be a bonus problem for those of you who want to kind of show off your skills. So, you know, if you want to do the bonus problem, you do the bonus problem. If you don't want to do the bonus problem, yeah, right? Read it. And ask any questions you have. Ask next class. So look for the project tonight or tomorrow. And I'll see you all in 2 days for more fun. Chapter 9. Bye, stream.